for this module 3 quick self-check, I'm going to again show the answers and then I'll come back and discuss each one in detail. So for the first answer, it is A, 2 is C, 3 is D, 4 is that the acceleration as a function of time is 24t squared I hat minus 6j hat. So we have both our I hat and j hat components. For 5, it's open-ended, but the main features are that in x, you have a constant velocity. So the initial velocity equals your final velocity. In y, you do have a constant downwards acceleration, so that initially it's going to slow down, and then it'll speed up. And because it goes off a cliff onto the ground, it's going to be faster at the end in the y direction than it was to start. 6 was a misleading question because the acceleration is the same and non-zero everywhere, so it is D. 7, problem-solving concepts that we've learned so far. There are 4 main ones, and they're they sound very similar, but you do handle them all very differently. 1D motion, constant acceleration, free fall. 1D motion, non-constant acceleration, calculus. 2D motion with constant acceleration, projectile motion. And 2D motion with non-constant acceleration. That's going to be calculus as well, but keeping our components separate. So then we have a ball shot sideways by a spring at the same time a ball is dropped. 8 is C and 9 is A. All right, so let me now go ahead and discuss each individually. So in this case here, for this first problem, we're throwing a ball off the roof of a building at a downward angle. That tells us that our initial velocity vector will be down. So the initial velocity vector must be down. And then it also has an acceleration that is always going to be downwards. So the acceleration downwards. So far so good for these ones that I'm highlighting. All have the acceleration down, and then these other A and B also have the velocity down. Displacement. Displacement is a vector that points from the start to the end. Remember from our vectors. That is what displacement is. So displacement also is going to point downward because that's the direction that the ball starts at the top of the cliff, ends at the bottom. All right, for 2, this came from the video on circular motion. And so the acceleration of this is going to be the sum, the vector sum of your centripetal acceleration plus your tangential acceleration. So at point P, it's speeding up, so it's pressing the gas, and so the car is increasing its speed. So there is a tangential acceleration, tangent to the circle, that goes along B, and towards the center of the circle, which is where D points, then there's going to be the centripetal acceleration towards the center of the circle. So the vector sum of these is really anything that's between the tangential and the centripetal acceleration. You can see that then C is the only option that's between both B and D. So B gives us the tangential, D gives us the centripetal, and the total acceleration will be the vector sum of those. All right, 3, it's another circular motion problem. An object is moving clockwise, and it's asked what is its velocity and acceleration when it's at this location. So first, just being very careful, always drawing things out. That location is x equals 0, y equals -4. So this is our point in question. So at that point in this motion, my velocity is always tangent to the motion, and my acceleration is towards the center of the circle. And so you can see that my acceleration is going to be in the positive direction, and my velocity is in the negative I hat direction. So just finding those correct orientations and signs gives us the correct answer. For 4, I'm going to go ahead and erase my answer so I have some space to work. In this case, I have a vector position in the x and the y, and I just then need to do calculus in the x and in the y and keep my components separate. So my velocity is just going to be equal to dr dt. So that's going to be equal to 8t cubed I hat, and then minus 6t j hat. And then I can get my acceleration, which is just the time rate change of the velocity, which is going to be equal to 24t squared in the I hat. That's my x component of my acceleration, minus 6 j hat. So I actually have constant acceleration in my j hat direction and a time varying acceleration in my horizontal I hat direction. All right, so for number 5, I've already basically gone through it. The highlights are that you need to have constant velocity in the x direction, and changing velocity in the y direction slows down on the way up, speeds up on the way down. And because it's going to be a not level launch, then it'll be going in y the same speed when it gets back to the same level, but then it'll keep speeding up in y as it goes, which makes sense because a really tall cliff, it would be going faster and faster and faster near the ground. 6, projectile launched at 30 degrees above the horizontal. Projectile's acceleration is greatest, and this is a trick question because the acceleration at all points is the same. It's the constant downward acceleration at all points. The velocity at any given point would be tangent to this motion. But the acceleration is this nice constant downward negative g j hat. All right, 7, I've already listed the main problem solving concepts. These are very important for when you have a combined concept problem. If you have a non-constant acceleration, you have to use calculus for that portion of the problem, and then you can combine it with our 1D or 2D motion type problems to get a final answer. And then lastly, ball shot sideways by a spring at the same time that one is dropped. These both have the same initial y velocity, which is 0. A horizontal launch and then a dropped ball have vy initial equals 0. So they're going to have the same time of flight. So the same time in the air. So that's why they hit at the same time. Now, which one will hit the ground with a greater speed? This is where we have to be careful. Speed is the magnitude of the velocity. So that's a magnitude of the final velocity vector, which is the square root of vx squared plus vy final squared. So even though they're in the air for the same time, they will have the same final vy final. Their final velocity in y will be the same. But the one that's shot horizontally has Vx is greater than 0 for the horizontal launch. So therefore, the speed of the one shot horizontally will be larger because it has an x component to that speed. All right, so as always, go ahead and make sure you clear up any questions you have with me before you end this module and take the Module 3 quiz.